we had started talking about the electric field, and again, it is a very abstract thing the first few times you see it. So I would recommend, if it's still not clear what it is, to go back through the recordings and make sure that it is clear because as we keep moving forward, we're just going to keep layering more and more stuff on top of it. So if it doesn't make sense, things are on a very shaky foundation for the next month or so until we move into something that's sort of like it's still actually building on top of it, but we just stop worrying about it building on top of it, I guess. So the rough idea of the electric field is that everything that is charged creates it, and if you dip something else into that space, it will feel an electric force. So the field is really the fundamental thing. Every charged object makes one. Forces only come about because of one thing dipping into another thing's electric field. Similar with gravity. Even if Earth were the only thing in the universe, it would have a gravitational field. But if suddenly you pop into existence somewhere near the Earth, you start to feel a force because you're now sitting in Earth's gravitational field. So a field is a one object thing, it's a property of a singular object. Forces are what happens when one thing enters the field of another. The force is an interaction between that thing entering the field and the thing creating the field. The strength or size of that force depends on how strong the field is and how large the thing that's entering it is. In this case, large just means how much charge it carries, but for gravitational fields, how much mass you have determines how large a force you feel from the Earth's gravitational field, how large your weight is. So it's a lot of parallels between electric and gravitational fields that I'll fall back on when things get too abstract for the electric side of this. If we have more than one object in the universe, which we definitely do, then we have to worry about net electric fields. What is the effective influence that multiple charged objects have on the space around them? And we can approach that in almost the same way. We just imagine that only one of those charged objects exists at a time, see what its field would look like, and once we've done that for all of them, add those fields together as vectors. And that's the real thing that exists in that space, the real electric field that we actually would feel if we stood there. Field lines are a way to start getting a sense of the shape of the electric field, and we do it by just determining the field at lots of different points with our little test charge, which again, the idea there is you pull out a little positive charge out of your pocket, see what happens to it, and then divide by the size of the charge you used, and that's what we define the electric field as. But if you keep doing that at lots of points, you start to get these field lines, this shape of the electric field. I'll come back over to this simulation for that. So I'll do the dipole this time. And so if we go back to the idea of you pull your little test charge out of your pocket, that's the white charge, and you see what happens to it. You see it's sort of moving away from the left-hand side, but now it's kind of creeping back towards the right-hand side. And you say, interesting, okay. Things tend to move away from the thing on the left, tend to move towards the thing on the right. That's what happens to my little charge. But you say, I still don't know what it's going to do if I just put this at a random point. So I'm going to just start doing a bunch more charges at once, throwing a bunch at it, little test charges, and saying, oh, okay, I'm starting to get the idea. They tend to get pushed away from the thing on the left and pulled towards the thing on the right. The thing on the right is going to be more like how gravity works. It sucks stuff in, but it's going to turn out to be a negative charge is what you're looking at on the right-hand side. But you say, that's still kind of a lot to look at. I'm just going to draw the direction those little white charges get pushed at each point. But I'm going to scale that by how large the white charges are, so I get something that only depends on the yellow charges making this field. And that will be these field vectors. But again, you say, okay, that's better. I can kind of see what's going on here a little easier, but that's still kind of busy. So I'm going to draw lines connecting these different arrows together. And that's our field lines. And now you can really see the shape of that electric field. It tends to be away from the thing on the left and towards the thing on the right. How can you tell that it's away versus towards? You can't really in this picture, but that's just because he forgot to include arrows on the lines. For us, we have our arrows saying whether it's away or towards. So that's what the field lines are doing for us, showing us the shape of the field around charged objects. They make that invisible thing. I know there's something going on around this guy, but I don't know exactly what. They're turning that into a visible thing. Now I know what's going on around that guy. He tends to push stuff away in all directions. This is just checking if the rules make sense. So we've got 4 cases for the same charges, and only one of them is the right way to sketch the field lines. We got to figure out which one is correct by figuring out what's wrong with the others. So let's look at A. What's wrong with that picture?
You have field lines crossing.
Yeah. What's the problem with that? Why is that a no-no?
You aren't able to tell the real direction that the electric field is going in.
Exactly. Yeah, and that's the point of field lines is they're supposed to tell you at each location in space which way does the field point. If we got something like this, it's telling us that the field both points this way and that way at the exact same time. And I don't even know how to interpret that. Again, it's like water flowing in 2 directions at the same point. How does that even work? And it's because it doesn't. All right, part B. Do you see anything wrong with that one?
The positive in the middle doesn't have field lines going towards the bottom electron.
So it does, but just not the right number. What would be the right number? Yeah, it really should have another one right here, but it doesn't. Why should it have that one? What tells you that it should be 2 instead of 1?
Is it the strength of the field?
It is trying to reflect the strength of the field, and that stems from the size of the charges. So if we want to properly reflect the strength of the field, we've got to draw enough lines to be proportional to each amount of charge that's present. So how many lines leave the plus 4q charge in this picture? Not with my sketched in one, but like the actual picture. How many lines leave it?
And that one, 8.
Yeah, 8 leave it. So a charge a quarter of the size of it should get how many lines?
2.
2. And that's why we know this one's right while this one is wrong. Because it's supposed to get 2 lines and it didn't. And also you notice up here, 5 enter this one. That's 1 too many for that one because it's half the charge of the 4q. So if 8 leave the 4q, 4 should enter the negative 2q. So 4 should enter, and 2 should enter. Lines aren't proportional to the charge. All right, we move on to case C. Do you see anything wrong with case C?
No.
We don't see any crossing of lines. What else looks right about this picture?
The number of lines going to each of the negative Qs are proper.
Yep. So the lines are proportional. If 8 leave the biggest 4q charge, half of that should enter a negative 2q, and they do. And half still of that should enter a negative q, because it's half the charge of the negative 2q. All right, and we could add on to that now none of these had this issue, but that lines leave the positive charge and enter the negative. If we had a picture where the arrows were reversed, that would be incorrect. So we don't have that issue going on. Part D has one additional issue that Part C doesn't. What's wrong with case D?
The lines are straight going into the negative 2.
Yeah, so that is the problem, but why is it a problem? Why is that not how it acts? What does the spacing of field lines tell you about the electric field?
Or how strong it is.
So the field right here, what should it be in comparison to how strong it is near these charges?
It should be weaker the further away you get from the charges.
Yeah, and how do you reflect how strong or weak the field is? For a weak field, the lines should
Be more sparse.
Yes. So that's the thing that's going on here is we would expect to have a strong field here and a weaker field here, but the lines are not telling us that.
The lines would say if they were straight that it's just constant, which it isn't, right?
Right, yeah, so we call that a uniform field, and we will see some examples where that is possible, but it's not possible for individual clumps of charge to create that. Field lines should spread out where the field is weaker. And again, I know it's weaker there compared to right by the charges because the charges are the thing making the field. It's going to be strongest near them, and as you move away from them in either direction, it should get weaker. Do have that working for us over here. Line spacing reflects the field strength. So this one looks good, and this one's out. So we are going to continue drawing lots of field lines. I'm not going to make you draw many, so that's not really why we did this. It's just to see the reasoning behind all of the things that we do draw. So you have to think of electric field lines as a map or a picture of something that's normally invisible to us. It's telling us about the electric field, which is a thing our eyes can't detect. So it's a very useful tool to have. And I'm going to give one application of electric fields. So it's not just a normal paint gun. It doesn't just spray paint. It sprays paint and it ionizes the air around it. And it does that with this little tip right here, this electrode. So they have a high voltage across that, and that starts to pull electrons out of the air. Call it an electrode. What does voltage mean? We'll find out in a couple chapters. But it starts to pull electrons out of the air, and that's going to make some of them stick to the paint droplets as they pass by. So our paint that's spraying out of the gun while this is happening is going to pick up a negative charge. Over here on the right is your workpiece, whatever it is that you're painting. And this is going to work best if it's metal, because if you have a negative charge that's approaching this piece of metal, what will happen to the electrons in the metal?
They'll be repelled, right?
Yeah, they'll be pushed away. So as those paint droplets approach, the electrons in the metal will tend to move towards the other side of it. They're not going to fly off it, but they will start to congregate on the other side. So a positive charge is induced on the surface of the workpiece, where those electrons just left from. And that'll happen across the whole thing. And that's going to help pull the paint in. The positive charge on the surface will attract the negatively charged paint and help it stick to the surface better than if you were just blindly spraying without this negative charge. The problem is that can only go on for so long until you start to get excess negative charge. You've got extra electrons flying in, and it's not pushing away enough electrons that are already there to leave some bare positive charge to attract the paint that's coming in. So what's going to eventually happen?
The paint's gonna start repelling from the
Yeah, yeah,
metal.
exactly. So eventually this actually stops working in our favor, works against us, and says, I don't want any more paint on my surface, even if it's not fully coated. So what you do is you give a way for electrons to bleed off, and we call that grounding the plate. And usually you'll see this symbol to say to the ground. Now that could mean just to a very large hunk of metal somewhere else, something that can collect a lot of charge, a reservoir for charge, or it could mean to the literal ground. It usually just depends on circumstances. And in electrical engineering, good luck because they use it for any sort of reference voltage a lot of the time, even if it's in no way touching the ground, or even if it's not metal sometimes. So that's fun. So that's why we do that. Grounding the workpiece lets some of that excess negative charge bleed off. And that means we can accumulate more onto the surface, spray more, and it will keep sticking. Eventually, we reach this steady state where just as many electrons are flowing off as are flowing onto the plate. And that establishes this electric field that points away from the positive charge on the plate towards the negative charge on the spray gun. And I'll probably do just every other charge. And at this stage, once we reach this nice sort of steady flow of paint, flow of electrons, these field lines sort of act as a guide for the negative charge, the paint droplets. Because which way is negative charge pulled relative to an electric field?
In the opposite direction.
Yeah, so those paint droplets now have a pathway. It's sort of a blind spray at first in the first few milliseconds of spraying, but now they have a guide, this electric field that's been established between the plate and the spray gun. So an electric field is established from the workpiece to the spray gun. And the negatively charged droplets flow opposite the field lines. There is one other neat thing about this, and that's that you actually get some of this induction effect that the negative charge pushes away some of the negative charge in the plates and leaves positive on the surface on the backside. And that means paint can actually wrap around the surface of the workpiece if you use an electrostatic sprayer. You can curve the bullet. And I'm going to come over here and show you that. So he's going to have it turned off at first, so the electrode is not ionizing air, it's just a regular spray gun. But then he'll turn it on, and you'll see the difference. So this is with it off. Now he turns on the electrode, starts ionizing the air. Those extra electrons help the paint bind to that workpiece surface. The ground, by the way, is the metal pipe that they're hanging off of. That's the big metal electron sink that extra charge can flow off onto. But see, this one didn't do so hot on the back. The one with the electrostatic sprayer, it's done. To me, that's so cool. Like, it's something that people almost get used to using in everyday life or seeing. Yet it's kind of magic. Like, it's curving the paint around the backside of this thing.
I have a question. Is it doing that because like the electrons are leaving and basically the positive charge is just wrapping around the entire piece?
The positive charge, as usual, it doesn't move. It's stuck in place. What's really happening is that even the electrons on the back side of the workpiece are being pushed away, and in particular being pushed towards the ground, so that they're bleeding off on both sides of the workpiece, allowing negatively charged paint to be attracted to it.
I was about to say, just making sure the grounding area kind of makes the workpiece have like a net zero charge.
Yes. Yeah, it gives a place for excess charge to bleed off to, so that essentially we think about how the explanation I gave probably made sense at first. Like, oh yeah, the negative charge is attracted towards the positive, it pushes off the negative. That only works until you get too much negative charge built up, and then that explanation breaks. This is almost like acting as a way to reset back to the original state that the explanation made sense for. It just keeps taking off that excess negative charge to where we're back to the beginning situation.
Okay, thank you.
Quick question.
Yeah.
So for the examples above the electrostatic
Mhm.
thingy, so the lines are pointing outward from the positive charge, but we also know that positive attracts negative. So why are the lines pointing outward instead of inward?
So remember that the electric field lines are telling you what that charge does to the space around it. And the general thing that positive charge does is it pushes stuff away. Now, when I say that, what I really mean is it pushes positive charge away from it. So any positive charge you set right here is going to be pushed away from the big positive charge. What would negative charge do? The opposite, like it always does. It gets pulled towards. That doesn't mean I have to redraw the field lines, because that's not changing the thing making them. It's changing what's responding to them. And it's just that negative charge happens to respond in the exact opposite way that positive charge does to electric fields.
Oh, okay, got it.
Yep.
So we're just looking at the positive charges moving outwards.
Yes, and really we're thinking about this thing and that its tendency is to push positive charge outward, and that's what we're plotting, is like the tendency it has to do that. It would do it for any positive charge, and it would pull things towards it for any negative charge. So to take it back to the gravity analogy, we're very used to actually this side of it, that gravity pulls stuff in.
Yeah, right.
We're not so used to this side of it. This would be like if there were a type of mass, there were some alien species out there that whenever they entered a gravitational field, they get pushed away from the Earth. And what's interesting is that is exactly what happens for electric forces and electric fields. It does work like that. You have two situations, two scenarios that can happen. We just haven't found an alien that's like that for mass.
Oh, okay. Okay, thank you.
Now that we know what the electric field looks like for a single point charge, which was all the way back up here, and we kind of know how we put together the fields of individual point charges, we're going to start using that idea, using the point charge as a building block. and using it to find expressions for the electric fields of more complicated things. The first thing we're going to look at is a dipole, which really is just two charges. So we know exactly how to do this. It's the vector addition stuff we did right up here, but for two charges. But I'm going to do it for a particular set of points. So what we did in that earlier example was I found the electric field at exactly 1 point in space, and it took so long to do. For this problem, I'm actually going to find the electric field at any point you want to know about it for along this axis, what's called the dipole axis. And that's just the line that's through the two charges. The reason I'm going to focus on that axis is because the math becomes much worse anywhere else. And this is just something to see sort of the power of this analysis. We can start to describe the electric field at many points using this procedure. We're then going to do the same thing, but for a ring of charge. So you place a bunch of charges in a circle. What does the electric field look like then? And then we're going to find the electric field of a disk. So now you've got charge smeared over an entire surface. This would be like, you're going to see capacitors soon, like a big circular metal plate. What kind of charge accumulates on there? What kind of electric field does it create? So we'll start with a dipole. A dipole is you've got the same charge, we'll say absolute value of Q, but those charges have opposite signs. And we place them some distance, I'll just call it d, apart. So you could place these charges a meter apart, you could put them a centimeter, a nanometer, and you see all of those different scales show up in nature. Your heart actually behaves like an electric dipole. It's one that spins around and around as your heart beats. I'm going to imagine this point P as being where I want to find the electric field at, but what you'll realize at the end of this is the particular point I'm looking at in the picture isn't important. This will work no matter which point along this line I want to know about the field on. So don't worry that we're picking a specific point at the moment. But at that location, what would the positive charge do? What kind of field does it create?
Repel.
I'm going to start pushing for us saying away or towards. I agree that if we set a little positive test charge right there, it would be repelled. But what's really important is the electric field, and that's just a way of measuring it. And the electric field is something that isn't a two-object thing, so repel doesn't really make sense. We would say away because it's a one-object thing. It's away from the positive charge down here.
Yeah, so we're drawing the field of P.
Not of P,
No?
at P. It's the
At
field
P.
of these guys at this location in space.
Oh, okay.
Yeah.
Okay, thank you.
It's like you have a gravitational field, or if you shuffle around your house with socks on, you build up an electric field around your body. It's your field, but the strength of it depends on which point P in space you're looking at.
Yeah, okay.
So I'm going to call this E+. This is the electric field of the positive charge. For the negative charge, what kind of field does it create at point P?
It pulls it towards.
Yeah. So again, there doesn't actually have to be anything there. The field is just towards the negative charge. We use a test charge as a way to imagine the electric field there and measure it, but the electric field exists even without doing that. It's a property of the negative charge, and its property is it's generally pointing towards the negative charge. Why did I draw it smaller?
Because the distance is further.
Yeah. So point P is farther away from the negative charge, and I can never remember if it's further or farther, to be honest, so I'm going to use both. So the net electric field is E plus E minus. But here, that plus is referring to vector addition. You add them as vectors and all the baggage that comes with that. So I'm going to go to describing it in terms of components, where I just use a plus or a minus. So if I'm in the positive direction, which I'll say is upward here, then I'll use a positive sign. If I'm in the negative direction, I'll use a minus sign. So E dipole is, well, E plus points upward. I'm adding it to an electric field that points downward. So minus E minus. And then, since those are both point charges, I know how to find the electric field of a point charge. So this will be like a side note. Recall that the electric field of a point charge is that size of the charge over the square of the distance from it. Or I could bring back that 1 over 4 pi epsilon 0 thing. So just remember this is k. It's the same thing. 1 over 4 pi epsilon 0. I'm going to write it that way, though, just because that's how you typically see it in terms of the epsilon 0 thing when you see the equation for the field of a dipole. So I could write this as, say, 1 over 4 pi epsilon 0, the size of the charge over r squared. And I know I can use absolute value here because I already took care of direction up here. I don't need to worry about what kinds of charge they are anymore because that's already dealt with. But one thing I do have to worry about is the distance. So if I come over here, the distance from the positive charge is this right here. Call that r positive. But the distance from the negative charge is a different distance. Call it r minus. So really, I have to call this 1 over 4 pi epsilon 0 and then q over r plus squared. And then minus 1 over 4 pi epsilon 0 q over r minus squared. So far, so good?
What is the epsilon in that 4 pi epsilon?
That's the thing that when we first introduced Coulomb's law, I was like, you could calculate 1 over 4 pi epsilon 0 every time, or just go ahead and put it in once for me, and that's the number k. So this was the one that's 8.85 times 10 to the negative 12. But when you multiply that by 4 pi and take the reciprocal, you get 8.99 times 10 to the 9th, the one you're used to seeing. Now, I don't like that I'm using slightly different coordinates to measure these two things. I'm measuring from different reference points, either the positive or the negative charge. I want to establish a common reference point. And so I'm going to pick the center of the dipole, midway between the two charges, as my common reference. And I'm going to start measuring this point P in terms of how far it is from the center of the dipole. That will be my coordinate, and I'll use z for that. So if z is a positive number, I'm on the positive side. I'm off over here from the positive charge. If it's a negative number, I'm on the negative side of the dipole. But if I'm going to do that, I need to rewrite the stuff I just wrote up above. So 1 over 4 pi epsilon 0 q over, so r plus, how would I write it in terms of z? Are r plus and z the same distance?
No.
No. I can relate them, though.
It'd be r plus minus z.
Almost. So what's this distance right here?
1/2 d.
Yeah, call it d over 2. So if I take this distance z and subtract that off of it, I get this distance, right? R plus is equal to z minus d over 2. And then we had to square r plus. All right, now I subtract off 1 over 4 pi epsilon 0 q over. All right, for r minus, how would you describe that in terms of z?
You would just do z plus d over 2 squared.
Yep, because r minus is d over 2 larger or longer than z. Now, I'm going to skip a whole lot of steps, a whole lot of algebra, because it really is a painful amount. I'm going to call it a ludicrous amount of algebra. In particular, it's so ludicrous that I will give 1 bonus point if you want to work it out yourself and turn it in, just on a sheet of paper. I know that AI is a thing, and I know that it's getting pretty good at math, but I would, for the sake of your own brain, recommend trying it out. Just make sure the algebra still works, because you'll need it. But it's going to come out to, and believe me, when you see what I'm about to write, you'll be surprised that it comes out to this. Q times that distance d over 2 pi epsilon 0 z cubed, and then 1 over, so this is all in brackets, 1 minus d over 2z squared, and all of that is squared.
Is that because we don't have actual numbers? But if we were putting in the actual numbers to plug into this, it wouldn't be that much algebra, correct?
Sure, yeah, if you wanted to stop here and put the numbers into that, you're perfectly allowed to. The reason I'm doing this is I actually want to make a simplification. I want to approximate something and make this a little bit easier to work with. The simplification I'm going to make is, let's always assume we are pretty far away from this dipole, meaning I'm standing some distance from it and I'm sitting in that field at a certain distance away. The size of the dipole is essentially that distance d, how far apart the two charges are. So what I'm really saying is, if I'm really far away compared to that distance, then I'd say I'm sufficiently far from the dipole for the field to simplify out a little bit. That's one way to think about it, is the field near the charges is a lot more complicated than the field all the way out here. It starts to sort of standardize. Like if you notice here, this actually is what we're looking at, is along this axis. This field is kind of messy. The field out here is going to start to look, and you can't see it in this picture, but it's going to start to look a little bit more uniform, a little bit easier. So for the sake of my own sanity and saving having to calculate so much, I'm going to make that approximation and say, let's focus on points z that are much larger than that dipole spacing d. So if you're pretty far away like that, look at this in parentheses. What's that going to be if z is way bigger than d is?
Really small.
Yeah. And by the way, it gets squared, and numbers smaller than 1 get even smaller when they're squared. If I subtract it off from 1, I basically get 1, right? Like 1 minus 0.000001. And then I square that. 1 squared is 1. And then I take that and I take 1 divided by it. Well, 1 divided by 1 is 1. So this whole thing in brackets is essentially equal to 1. It's approximately 1. And you've just seen, maybe for the first time, what's great about physics that mathematicians don't get to do is they get to approximate. They get to choose how hard they want to make their life by deciding what to keep and what to throw away. And it very much is a acquired skill of when to do that and how much to do that. But it's a whole area of physics and math. It's called asymptotic analysis, or you hear about something called perturbation theory. But anyway, if that whole thing in brackets is 1, then really E dipole is just the stuff out front. And so let's kind of check ourselves, see if this makes sense. Does it make sense that the electric field of the dipole is stronger if both charges become larger? Because both of them have a size q.
Is it based off of the other charge or the dipole?
It's either individual charge. One is a positive of that amount, one is a negative of that amount.
Okay.
Does it make sense that the farther apart the two charges making up our dipole are, the stronger the electric field they create?
Yes.
Okay. That one, it may be a little bit trickier to think about that one, but just think. If the two charges were right on top of each other, what kind of electric field would we have?
There'd be no field between them.
There would be no electric field because you neutralized the field out. You have a positive and a negative, they are neutral. The net charge is 0, and so the field should be 0. That's what happens when D goes to 0. When you space the two charges out, put them far away from each other, you're essentially making it harder and harder for their fields to cancel each other out. So the net field is larger. And then finally, z is in the denominator. That's how far away you are from the dipole. So not how far apart the charges are from each other. That's d. But how far away you are where you're measuring the electric field, does it make sense that the farther away you get, the weaker the field gets?
Yes.
But there is something interesting to take away from this, and that is z cubed, not z squared. Meaning that if you get twice as far away from a dipole, its electric field becomes 8 times weaker, 2 cubed. Whereas if you get twice as far away from a point charge, its field becomes 4 times weaker, 2 squared. So the field of a dipole dies off much faster than the field of a point charge. And it's because you have one positive and one negative. If you're standing really far away from them, it almost looks like they are overlapping, even if they are separated, even if D is not 0. When you're standing real far away, you can't tell. They look like they're overlapping, so the field should be pretty weak. And I could write it one final way, and I'm going to do that in terms of this thing called the dipole moment. It says essentially something about the size and strength of the dipole. Size is built into that number D, strength is built into how much charge there is. So we could write this as P over 2 pi epsilon 0 z cubed. P is sort of like a sticker you can put on the dipole. Like if you're buying dipoles at the store, they'll have different values of P for different use cases. If I want a really strong dipole, I'll pick a large P value. If I want a weak one, I'll pick a small P value. But it is something intrinsic to the dipole. We could define a vector, and this is actually more important for what we're going to do on the next page. We're going to define what's called the dipole moment vector and say it points from the negative to the positive charge. So as of right now, there is no rhyme or reason to why I'm doing this. So don't feel like you're lost on why I'm defining P. It will make more sense on the next page once we get into it. Just to sort of sketch the whole thing in, got a plus, got a minus, that dipole moment vector, and then our field looks like this. Points away from positive towards negative. So that's what the electric field looks like, but we only know a value for it. We can only put a number to it if we're along this line, along the dipole axis. That's what we did on this page. If you want to know about the field over here, have fun with that. It's going to be a lot more trig. Okay, any questions on that one?
Where would we use dipoles in like real life stuff?
Antennas are essentially dipoles. So they are charged sloshing back and forth between the two ends of the antenna, and that generates electromagnetic waves, and they travel through the air, and then they get caught by another dipole antenna, sloshing back and forth. That's one of the biggest uses.
Copy, thank you.
And then again, the human heart. Now, I'm not saying you'll use the human heart, I hope, even for the bio students, but the human heart essentially is a dipole that spins around and around and around inside your body. The heart doesn't, but the electric field it creates does. So that was a question of, if we have a dipole, what kind of electric field does it create? What influence does it have on the space around it? This page is about, if we put it into an electric field created by something else, what influence is there on the dipole? What will it do in that external field? And it's kind of interesting because dipoles, unlike point charges, they have both kinds of charge. So they kind of do both things at once. So we got a positive, we got a negative. If we put them in an electric field that points to the right like this, and we don't know what's making this field, but it's probably there's some kind of big glob of positive charge over here, so the field lines point away from it, and then some glob over here of negative charge, the field lines point towards it. But again, we don't need to draw them anymore. The field is the important thing to know about. What will this part of the dipole do in that electric field?
Go along with the field?
Yeah, it'll be pulled to the right. So it'll feel a force. I'll just call it F. What about the negative charge?
Go against the field.
Yeah, it'll be pulled to the left. But since those charges are the same size, and remember the force on a charge is proportional to how big it is, how much charge, and then the electric field it's sitting in, what's the net force on the dipole?
0.
0. Each charge feels the exact same force, so the net force on the dipole is 0. And I'm going to call that the net external force on this system, because it is a system of two objects back from Physics 1. If you remember talking about systems and Newton's law for systems, this will be familiar. If not, you may want to look back at that before next class. But we have positive F, that's the force on the positive charge. And I know I'm out of time, I'm just going to write this line. And then minus F. Add up to 0. But in general, Newton's second law says that the net force on a system of particles is equal to the mass of the system times the acceleration of its center of mass. And we'll see what consequence that has next time. Check chat. Will we be having a quiz soon? I'm hoping we're back in person on Wednesday, and if so, then yes, the quiz on chapter 21 is on Wednesday. If we're not back in class on Wednesday, then the quiz is on Friday. If we're not back in class on Friday, it's on Monday. You get it. It's just whenever we get back.
So is the quiz going to be just conceptual, or will it also have calculations?
It's all conceptual.
Homework be posted on this chapter yet, or will it be once we finish with chapter 22?
Once we finish, so the graded practice for this chapter is up, but not the homework. All right, well, everyone have a good day. Stay safe, don't slip, and hopefully this will all melt very soon.